Hello, today's lesson is going to be on correlation and a little bit later on regression, which is the idea of lines of best fit. This topic is mostly notes based, it's mostly definitions and learning key concepts, so there aren't really much in the way of calculations to be done in the year one correlation thing. In year two, we'll look at a slightly more mathematical approach to correlation, but in year one, it's mostly just understanding the key concepts. Quite a few of these you've already met at GCSE. So the idea of correlation is anytime we have bivariate data, which is data that has two different variables, so x and y. We've previously been using one variable data where it's just x. We can plot these on a scatter graph and see if there's some kind of a relationship between them. We name these two things. The bottom one, the one that goes on the x-axis, is either the independent or explanatory variable. These are the variables that usually we have free governing over, or the one that affects the other one. We've then got a y-axis, which is our dependent or response variable. So this is usually the one that's affected by the other one. So breaths per minute is likely to affect your pulse rate. Maybe it's the other way around with this one, it's not very clear cut. But quite often you get a decent, this one is probably going to explain this one. Correlation, you've met this idea before. We can have no correlation in the middle. And if we go in a line going upwards, we start to get positive correlation. So this is weak and then strong. And going this way, we have weak negative, which is not completely in a line, but still a general trend going downwards. And this one here is strong negative. So this is the idea, negative correlation. As x increases, y goes down. And positive correlation, as x increases, y goes up. So I'll give you a bit of time to add that to your notes. If you want to pause it, you can. So we use this idea of a causal relationship. Just want to make sure you're not misreading this. This is not a casual relationship. This is a causal relationship, which means one variable causes a change in the other one. So just because you've got a correlation doesn't necessarily mean that one thing causes the other. There might be another factor. There might be something we've overlooked. There might just be luck. It might be a case of finding two things that happen to have the same pattern. Okay. We're going to have a look at two examples here. I'm not going to write anything down for these examples because they are mostly explain and describe questions. So for this one, we've got a scatter graph. Here's one that I took earlier from the answers. So all of this is doing is drawing our scatter graph. We've drawn our x ones going up to, so our y ones going up to 60, because this one goes up to 50 odd. This one goes up to 4, so a little bit further here to get to enough room to get everything on. And we can see here we have weak negative correlation. So draw our scatter diagram A. Here is our scatter diagram. Notice it's got a labeled axes. It's got units on its axes. It's got a title. Describe the correlation between distance and population. Well, as the distance here gets bigger, this one's coming down. So this is negative correlation, and it's not a perfect straight line, so it's quite weak. So this we call weak negative correlation. For part C, we're asked to interpret our answer to part B. Interpret means to explain, using the context in the question, why this is the case and what this actually means for the question in general. So as the distance here increases, our population density decreases. So answer for part C is going to be a sentence along the lines of, as the distance in kilometers from the city centre increases, the population density, you could put in people per hectare, decreases. Or something along the lines of, the further you are from the city centre, the lower the population density is. So that's the difference between describe, which is weak negative, and interpret, which is as the distance goes up, the population goes down. You need to make sure that you have these words describe and interpret the correct way around, because if you write an interpretation for B and a describe for C, you won't get the marks because you've not done either of the two things asked in the question. This one here is about a study, so it's a study of 14 people who are all of her friends, and she's trying to work out if the age at which you end education and training affects your hourly pay at the age of 25. So this is something you're all probably thinking about when you go and leave here, if you go to university, if you go straight into a job, what's actually going to give you the best pay prospects. So describe the type of correlation shown. Here we've got something that clearly doesn't fit the pattern, but in general we have weak negative correlation here, which would suggest that the longer you spend in education or training, your pay at age 25 is actually likely to be lower. It might pick up again afterwards. This might not be a straight linear correlation. This might be an unfair sample. This is only 14 people anyway. This person here, maybe they did some different training. Maybe they're very successful at their training because they've clearly got the highest wage out of all of the people here, and they spent the longest time in training. So describe the correlation, I would go with weak negative. This person says her data supports the conclusion that more education causes people to earn lower hourly rate of pay. Give one reason why this conclusion might not be valid. I can think of several of them just from looking at this. This is a sample of 14 people, and they're all her friends. So this is a small sample size. So for number one, one reason why it might not be valid is the sample size is very small. They're all her friends, so this might be a biased sample. It might be that all of her friends were really bad at education and training, and the more of it they did, the lower their wage was. And this person might be good at education and training, so we don't really know. There's also an outlier here which could require a bit more investigation. So maybe this is evidence of a different trend. So 3 things we could notice we're asked to give 1. Sample size, it's too small. Sampling, she asked her friends, this is not going to be a fair sample. And this outlier here, there might be a different trend that we're not quite picking up from our current sample. Have a go at some of these questions. Pause the video here if you want. These are all answer the question ones. You are probably going to end up writing sentences for a lot of these, and very few of them require any kind of calculation at all. For the second part of this lesson, we're going to have a look at regression. This is an idea for finding a line of best fit for plots pointed on a scatter diagram. So this is actually formally called the least mean squares regression line, but we usually just call it regression for short. And all this does is it finds the line that has, if you find the distance between the vertical distance between the line and these points and square them all and add them all up, it minimizes this. So it's basically the best possible line of fit calculated using maths rather than by eye. Because if you've ever tried to add a line of best fit to a graph, sometimes it's quite tricky. Sometimes they're all in a perfect line and it's easy, but sometimes it's actually quite tricky to work out where this line goes. So this is called a regression line. There are a couple of facts here about regression lines. I definitely add these to your notes. I'm just going to run through what each of these things mean. So a regression line of y on x is the form y equals, this is mx plus c, but we write the constant at the start. So this is basically y equals c plus mx. We'd normally write it the other way around, but this is the traditional way for writing regression lines. So b is the gradient, and it tells us how y will change if you increase x 1 unit. Because that's what the gradient is. If you go along 2, you go up, you go along 1, you go up whatever the gradient is. If the gradient is 2, you go along 1, you go up 2. So this can be used to give it an x value and predict a y value, but it will not work the other way around. If we go back to here, this is because it gives us the best possible y value, because this uses vertical lines. Not covered in this course. If you wanted to use it the other way around, you'd have to do a regression line going this way, and you might get a slightly different line. So you might get a very slightly different estimate if you wanted to go the other way around. So you can go from x up the line and get a y value, because this minimizes the y error, but not the other way around. So you can use x to predict y, but not the other way around. If you pick an value for x that lies inside our data set, it should be accurate. This uses the idea of interpolation. So just to go back here, if you pick something between x1 and x4, it should be in this area in the middle, and it should give us quite an accurate answer. Picking something outside of our data set we call extrapolation, which is unreliable because we have no idea if the trend in data continues after that. Most of the questions we're about to answer come down to one of these 4 facts, so I'd make sure these are in your notes before you carry on. 2 quick examples, and then we'll have a go at some of the questions. So here we've got a scatter graph drawn from the large data set, which is a big set of weather data that's provided as part of the course. You can find this on Moodle in the large data set area if you want to have a look at the actual thing, but it's basically just a big set full of data. So this covers maximum gust and the wind speed for some places in Camborne in 2015. So describe the correlation we see on our scatter graph. I would call this strong positive correlation. It's not very strong, but it's pretty good. It's pretty strong correlation. So I'd either call it strong or strong positive correlation. So positive or strong positive correlation. The equation of regression line for G on W for these 15 days is, so here's our starting value, here's our gradient. So this line starts at 7 point something, and every time you go along 1, it goes up 1.82. Give an interpretation for the value of the gradient for this regression line. So this is, as W, the wind speed increases by 1, the gust increases by 1.82. So every additional 1 knot of wind speed would lead to a gust increase of 1.82. This next bit asks us to justify, so explain why we're allowed to do a linear regression line for this instance. And this is simply the points lie on fairly close to a straight line. Because the correlation is quite strong, if we were to draw a line through here, the points would lie fairly close to this. So it does look like a straight line is going to be a good model in this instance. So for the justification, I'd make sure you mention strong correlation, because this does look like they do seem to lie on a line. It's a bit more of a deviation towards the top, but certainly these early points, they look quite linear. So these are all explain questions. We didn't have to do a single calculation for this. For the second example, we are given some data about head circumference and gestation period of newborn babies in a clinic. So there are only 8 here, so we're going to get a bit of deviation because it's quite a small sample size. So we've got a scatter graph. We can see there is a bit of deviation, but we can draw this line of best fit here, which looks reasonable. The equation of our regression line here is, so we've got our start value here, plus we've got a gradient of 0.624. So as the head size, as the gestation period increases by 1, the head size increases by 0.624 centimeters in circumference. So a regression line is used to estimate, and we can estimate by plugging in x values, the head circumference of a baby born at 39 weeks. So if we were to put 39 in here, we could get out an answer for y. And looking at our data, born at 39 weeks, that's gestation period. 39 is in keeping with our set of data. If we have a look in here, 39 would be here. Moving up, we'd get something here. Actually, this one maybe was a bit of a small baby. It should have maybe been very slightly bigger for our line of best fit. But 39 would give us a reasonable estimate. When we come to look at 30 though, 30 is outside our set of data. Because if we look here, we're looking at x, not y. So this 30 here is a y value. So we're looking at 30 weeks gestation period. There's no 30 in here. This actually starts at 33. So this is going to give us an unreliable estimate. So this is extrapolation. It's outside of our data set. It's actually over here. And we don't know what happens to this set of data. It might be that babies are only born from 22 weeks, because this one starts at 23. It might be that they don't grow a head until week number 32. So we actually don't know what happens with this data set if we start going beforehand. So 39, accurate, it's interpolation. And 30, inaccurate, it's extrapolation, it's outside of our data set. A nurse wants to estimate gestation period for a newborn baby with a head circumference of 31.6. Explain why we cannot use this regression line. So this is using the fact that this here is a y value rather than an x value. So this line, which is y on x, can only be used to produce an estimate for a y value, and here we're being asked to produce an estimate for an x value. So this is not a suitable use of the regression line. Once you've got these added to your notes, I suggest having a go at some of these for 4B. Reminder that all the answers are in the back, and the online version of the textbook has full explanations about how all of these things work. This is mostly all concepts, so you might want to do it with your notes out in front of you.